we will be set. All right, so I wanted to have the exams graded this weekend, but I did not get as far as on that as I wanted to. So it might not be until this weekend that I can get to finishing grading your exams, and I'll give them back to you and we'll talk about everything about them. So today we're going to talk about Pipeflow again. We had a class on Pipeflow before the exam, but the material on it wasn't covered on the exam, so I would understand if it kind of fell out of your brain a little bit. So let's start with a review. So we learned about this relationship for flow in a pipe. Does anyone remember where that came from? We derived it from something. Anyone remember how?
The Reynolds number?
No, the Reynolds number comes in eventually, but we started without that. We started from sort of like looking at the system fundamentally.
Did we start with?
We did a kind of
balance.
A balance, Tyler. What kind of balance?
We did a force balance on the pipe.
We did a force balance on a pipe, where so the pressure creates a force pushing forward, and then the shear stress on the walls of the pipe creates a force that pulls back. And these balance, and this helps us see that the drop in pressure over a length of pipe can be found from the shear stress on the wall of the pipe. That's sort of where it comes from, is from that friction on that pipe wall. So we also learned this equation for friction factor, but where did it come from? Or when can you use this one? There are certain situations in which you can use this specific equation for the friction factor. What is that situation?
Laminar and circular pipe?
Yes, laminar flow in a circular pipe. Do you remember what you would do if the pipe wasn't circular?
There's a table with corresponding values that pertain to the ratio of the sides if it's a square or rectangular pipe.
Yes, Avonlea. You have to go and you have to look up a different formula for whatever the shape is. Rectangles are the most common. And then you also need, when you're calculating the Reynolds number, you need to use the hydraulic diameter. So this isn't something we do a lot. Most pipes are going to be circular, but that is what you would do if they weren't.
Dr. Nickerson?
Yes.
I'm kind of confused about, so when you have, say you have a pipe and there's no velocity change and no height change. You have, I'm just kind of confused about how you have a change in pressure term and also pressure loss term.
Okay.
So I guess the relationship is, if there's no pump, then the change in pressure is equal to pump loss. But if there is a pump, the change in pressure will be 0, and the pump loss and the pump and the loss will be equal. Am I saying that right?
You are saying that right, but you're not generalizing it enough. So you're in the right direction, but the general point is, so let's say that we had like a tank over here that's open, and then like a tank over here. So let's say this is P atmosphere and this is 2P atmosphere or something, and there's a pipe in between them, right? So if it was like this, then when I would be setting up my mechanical energy balance, it would be 2P naught minus P naught, okay, plus 1/2. This is my 0.1, this is my 0.2, plus 1/2 delta alpha v squared plus rho g delta z, there's a rho there too, equals pump pressure minus pressure loss, like that. Okay, so I set up my mechanical energy balance, and in this case, the change in the velocities is 0, and the change in the height is 0, and there's no pump. So we would just end up with, actually, you know what, never mind, I'm gonna put a pump in here. There's a pump here. Okay. So I put a pump here, and so the balance would be from point 1 to point 2, P2 minus P1 plus 1/2 rho delta alpha v squared plus rho g delta z is equal to delta P pump minus delta P loss, like that. Okay, so then like blah, blah, and I would get something like 2P naught minus P naught equals delta P pump minus delta P loss. Okay, so if we were just doing the balance from like right here to right here, like if I called that point 3 and point 4, then the change in pressure between point 3 and point 4 would just be delta P loss. Like the only place that change in pressure would come from would be from that frictional loss. But if we set it up some other way, so in between point 1 and point 2 that I've drawn here, then the change in pressure comes from both that frictional loss over the pipe and from a pump. And it would be the same thing if it was like lifting it up or down or whatever. You would just include that in the equation. So if we just do the balance over a pipe with no pumps and no change and no anything, then delta P is just delta P loss. But if we do the balance over a whole system that just has a pipe in it, then there's other things that would contribute to the overall pressure change.
Okay, cool. Because I think earlier I thought that delta P loss was P1 minus P2. That's only the case if there's nothing else going on in the middle, right?
Yep, that's only the case if there's nothing else going on.
Okay.
Okay.
That makes so much sense. Thank you.
Thank you. Okay, so we also presented this equation here for pressure loss as a function of the friction factor. And then this one, which is just pressure loss expressed as a head loss. So do these equations depend on whether flow is laminar or turbulent?
Aren't both of these only for laminar flow?
Nope. That is why I asked this question, because this right here is just for laminar flow, telling you what the friction factor is, but these equations with the friction factor work either way. Okay, so how to get the friction factor will change, but these equations don't, because these equations they actually just came from this same balance here, and that doesn't change. Okay.
And I have a question based kind of on that force balance. So I understand that when we're talking about the force that's acting on the wall, then we include that shear stress because that's pulling on the wall. But in what sense does the pressure times the cross-sectional area work on the walls of the pipe? Are we doing the balance? I guess, are we doing the balance on the walls of the pipe?
No, we are not doing the balance on the walls of the pipe. We're doing the balance on, so what we would call the control volume here is that we're just kind of cutting out a volume out of space. And that volume would be some section of the pipe, okay, like this. And so the walls of it are all around the side, but then on the walls of it go around, but then on either side you have this vertical surface that's actually just like just imagine a slice through, and the pressure pushes on that. So technically the pressure also pushes all around here, but it doesn't matter for what we care about.
Okay, Yeah, that's what I was wondering, is if we were doing it kind of on just the shear stress on the wall, or if we were really looking at kind of a disk of fluid in that pipe
Yeah.
and doing a balance on
Yeah.
the disk of fluid.
It's more like that. It's more like on the disc of fluid, and the fluid is touching the wall around the sides. So that's where that happens. Because
Okay, and
the wall drags back on the fluid, right? So
Mhm.
so it's more like the balance is on the chunk of fluid.
And how does this equation take into account that that force due to the shear stress on the wall is different depending on how close to the wall you are? Like where is that
So,
reflected in this relationship?
well, it's at the wall is where that force comes from. So shear stress acts all the way through the fluid, but with the fluid sort of pulling on itself, but it is significant. It is most significant at the wall, okay? And that is where the significant friction arises from. At least when it comes to the energy balance. So the friction that really affects the energy balance happens at the wall, because that's where the shear stress is most prominent. So that's where the viscous forces are most significant. So
Okay.
it's just at the wall. It's at R is equal to big R. That is how mathematically it would be.
Okay.
Okay.
Sounds good.
All right. So that is how you would get friction. So these equations work for laminar or turbulent flow, or non-circular pipes, or whatever. So you would need to use the hydraulic diameter in that case. We learned how to get friction factor for laminar flow, but as we've said before, most flow is turbulent. So we want to figure out what will happen for turbulent flow. Okay, this right here is called the Moody Chart. And the Moody Chart is almost the classic way to find friction factor. People have used it for decades or 100 years. I don't actually know. I should look that up when this was invented. Point is, this is sort of the classic way of finding the friction factor. If you open up Perry's handbook, this will be in there. And and these relationships that we see on here are experimental. Okay? So these are an experimental relationship, just like we saw like drag coefficient as a function of Reynolds number. That was an experimental relationship you would see on a chart. Same thing here. Something else I want to point out is that friction factor and Reynolds numbers, these are both dimensionless groups. And remember how we said when you non-dimensionalize an equation or a relationship, one of the reasons that's useful is then you can just put one chart like this instead of having to do a chart for every single liquid and pipe size on the planet. Instead, you can just have one with the non-dimensional parameters. Okay. We're going to talk about a few of the things that this shows. So from this chart, what kind of things does the friction factor depend on? Looking at this chart.
Density.
Okay, density, the properties of the fluid that gives us Reynolds number. Let's sum that up as Reynolds number, which includes, so that's the density, the viscosity, and the speed, the average speed through a pipe that comes together to Reynolds number. What else?
It also depends on the pipe roughness, because you can see different curves depending on how rough the pipe is.
Mm-hmm. Yep. So pipe roughness, which we'll talk a little bit more about that. And so on the, what else?
The length of the
Well,
pipe.
whether it's laminar or turbulent, right? What, Connor? Sorry? Connor?
The
You leaned
length of
forward.
the pipe, perhaps.
Oh, the length of the pipe, yeah. So actually, the length of the pipe does not change the friction factor. the length of the pipe, once you have the friction factor, the length of the pipe will tell you what the total pressure drop is over this, but the length of the pipe is not here. Whether it's laminar or turbulent was the other thing I was fishing on. So laminar or turbulent, because you can see laminar is here, and these ones are turbulent. By the way, this part, this only works for round pipes, but the turbulent ones work for all shapes if you use the hydraulic diameter to get the Reynolds number. Okay, so the Reynolds number, which includes all of the things that are included in the Reynolds number, and the pipe roughness. And if those things will all determine what the friction factor is. So remember that the friction factor is defined this way. We did dimensional analysis to figure out what the friction factor would be by non-dimensionalizing that shear stress on the wall. So velocity profiles affect what the friction factor is going to be. So these are velocity profiles for laminar and turbulent flow. Just looking at this, if we assume about the same average velocity, for which of these do you think the shear stress will be bigger? Going by the velocity profiles, what's the relationship between shear stress and velocity profile?
The left one, because
Oh, go ahead. The greater the change in velocity over the change in the height, the greater the shear stress.
Right, Rankin, exactly right. Change in velocity over change in height, also known as shear rate. Okay? Or in this case would be ddr. Yes?
What is that symbol to the right of the F?
That is a proportional to symbol.
Okay.
Yeah. F is proportional to, and I say that because remember there's a number in there. I believe it's 8 for the Darcy friction factor, but doesn't matter. Proportional to. Okay, so Rankin, you were right. So for which of these profiles, Rankin, do you think the shear stress then will be bigger at the wall? Which do you think will have a higher shear rate at the wall?
The one on the left.
The one on the left, why do you think that?
Oh, I thought there was a greater change in velocity, but wait, at the wall. What do you mean by that?
Yeah, at the wall. We're looking at how big the change in velocity is per R at the wall. So which of these do you think has a bigger change in velocity at the wall?
Yeah, it would be the one on the right.
The one on the right. So and I brought that up to sort of show that you can see when we transition from laminar type flow to turbulent type flow, there's sort of a transition region where it could act a little bit like each, and the friction factor jumps up. So we suddenly jump up and have more friction loss. Okay, and then, of course, so, all right. When we non-dimensionalized the shear stress, what we were doing is using some kind of scale on it, okay? And the scale for shear stress is sort of V over D. So you take your velocity, put it over the diameter, and you have a scale there. And then, so as V average over D gets bigger, shear stress will get bigger. And then rho V squared, which is what we non-dimensionalized it with, which is kind of a pressure scale, is what that is. That scales with kinetic energy or with pressure. So which do you think will get faster as Reynolds number gets bigger? So remember, Reynolds number is rho VD over mu. So which do you think will get bigger faster, rho v squared or v average over d? E over d or rho v squared? Which do you think gets bigger faster?
Rho v squared?
Rho v squared, right? Because it's got that v squared in it, as opposed to v average over d, which as Reynolds numbers gets bigger, this will get bigger some, but rho v squared will get bigger faster. So as Reynolds number gets higher, do we expect the friction factor to get smaller or bigger?
We would expect it
What?
to get smaller because as Reynolds number increases, the denominator is increasing faster than the numerator.
Yep, exactly. So I just wanted to relate this back to the kind of thinking we talked about when we talked about dimensional analysis, and we said you can compare the scales of different things and how fast they get bigger or smaller. Does everyone remember how we did that? Anyway, just sort of want to connect this back to that kind of thinking. And that's why when we look at here, we see that as Reynolds number gets bigger, the friction factor gets smaller. Anyone uncomfortable with that or have any questions? Cool. All right. Roughness. So we talked about it, let's talk about it.
Dr.
Okay,
Nicholson,
so
sorry.
yes.
I do have a quick question. Back to like the last slide with like that chart. Can you like tell us how we should like read it?
Oh, so the way you would read it, so first of all, you probably won't use it most of the time in this class.
Oh, okay.
Because we're going to learn the equation that's fit to the data on this chart. But how you would read it is you would calculate what the Reynolds number is for your flow, and then you would calculate what the relative pipe roughness for your pipe is, which depends on the material. See, right here. And so you find your Reynolds number, you find your pipe roughness. So let's say it's 5 times 10 to the 5, and let's say this was your Reynolds number. So you would go up here, and then you would go over and find the friction factor. That's how you would read it. Okay, so roughness. Roughness is a length scale because it's sort of you can think of roughness as sort of little bumps on the edge, on the wall of the pipe. Okay, and the rougher it is, sort of the longer those bumps will be. So that's why it's a length scale, and it's in length units. So then we take that length scale and we put it over d, the diameter of the pipe, to get us another dimensionless parameter, another dimensionless ratio. For smooth pipes like glass or plastic, we would just say 0. And for other materials, you can look it up. So your book has a table. This friction factor chart has a table, and usually it's less than 1 millimeter. So you will usually see this in lengths of millimeter, and for English units, probably inches is what you would see it in. Okay. Something about roughness. Roughness matters for turbulent flow, but not for laminar. So the laminar flow, F was equal to 64 over Reynolds number. There was no roughness in there. Okay. Why is that? That is because turbulent flow has all these little eddies in it. And these little eddies are small scale. So sort of the length scale of these little turbulent eddies is similar to the length scale of the roughness. It's on the order of 0.01 millimeters or something like that. And so the roughness is going to change turbulent flow and turbulent velocity profile and all that things more than it does in laminar flow. Okay, that's just a way to remember why pipe roughness matters for turbulent flow but not for laminar flow. And if we look back here, so here's the relative pipe roughness, and we can kind of see how things that seem like they would be rougher tend to have bigger roughness factors. So for example, this takes glass and plastic to be 0.0025 millimeters. So as I've said, a lot of your book puts it as 0. It's probably close enough. Rusted regular steel is 0.1 millimeters, whereas rusted steel is 0.5, concrete 0.25, new smooth concrete 0.025. So in general, things that are rougher and cause more friction and more loss will have a higher roughness factor. All right, so as I said, that's what you saw there, that Moody chart, that's an empirical correlation that came from experiments. And the equation that is fit to the empirical correlation is this guy. It is called the Colebrook equation. I'll give you some time to write it down. This is going to be important.
So just to make sure, because we don't see log very often, that's going to be log base 10.
Yep, that's log 10. It's log 10 unless, when I write log, I mean log 10 unless I write something else on it. Okay, so this is the Colebrook equation. You will notice something about this equation that makes it kind of nasty. What do you notice?
The friction factor is on both sides.
The friction factor is on both sides, so this cannot be solved explicitly. It is an implicit equation which requires iteration. Now, back in the day, like when my grandfather was an engineer, you did iteration yourself. So what you would do is you would guess some value for your Reynolds, for your friction factor, and then you would put it in, and then you would use it to get a new velocity, which you would use to get a new Reynolds number, which you would use to get a new friction factor, and then you would keep doing that until your answers started to converge, and you would do that yourself on hand. But we live in the future, and we have tools for that. We have iterative solvers. You guys took 263. What kind of iterative solvers did you learn how to use?
fsolve.
fsolve and Python. Did you learn how to use solver in Excel too, or are we not teaching that in 263 anymore?
Yeah, we use Excel too.
Okay, Excel solver, fsolve, and Python, both great. I probably prefer fsolve myself. I feel like it's a little bit less finicky than the Excel solver, but both would work. Anyway, point is, y'all know how to solve an iterative problem. Okay. And then, all right, but in order to make it easier, you can also use what's called the Holland equation. This is an approximation of the Colebrook equation that is explicit. An explicit approximation is right here. The results are about 2% different, so it is less accurate. It's about 2% different. That difference usually is not a difference that we would make that would be significant to the kinds of problems we're solving, just because 2%, we make a lot of assumptions that probably make about a 2% difference, frankly. However, this is a more accurate one, and I want you to know how to use it. And there could be situations out in the world where you want to be as accurate as possible, and a 2% loss in accuracy would be a significant loss. Okay, so I want you to know how to use that, and you will.
So on tests and stuff, do you want us to use the Highland?
So, it depends. So in tests, usually I say you can use, I will usually say something like, the accuracy demanded by this problem means that an explicit approximation will be okay. And I'll tell you that. Just because I've never let you use Python tools on tests before, and so that is what I will say. So I won't say use the Holland equation. I will say an explicit approximation would be okay there, and I want you to know what that means. Okay. Alrighty. All right, so there's a few common types of fluid flow problems, and we're going to talk about how you would solve each of them. So let's say you know a length of pipe and the diameter of the pipe and the flow rate through it, and you're trying to find the pressure drop across that pipe. Okay, that's a common type of problem. Another kind would be, you know the pipe length and diameter and the pressure drop, and you need to find the flow rate that would get you that pressure drop. So let's say, for example, we can't have a pressure drop of more than 50 psi for our application, or the pump won't work, something like that. And then you want to find a flow rate that will give you that. If you know that that's the maximum pressure loss you can have, then you know you can't get a flow rate above some number, and you want to find what that is. And another thing you could do is, what if you know the length of pipe you need, you know the flow rate you need, and you know a pressure drop, and you want to find a diameter of pipe that will give you that. So your application needs some pressure drop, it needs some flow rate, you need to make it work, so the only thing you can do is try to pick a pipe diameter that will give you what you want. Okay? Let's go through and talk about how you would solve each of these. So the first type, you know length and diameter, and you're trying to find pressure loss at flow rate V dot. So what do you think you'd do first? Let's have someone who hasn't talked yet, like Tyler Green. Hi, Tyler Green.
Hello.
How are you?
I'm well.
So what do you think we'd do first? Just as a reminder, the equation for the loss is like that.
Okay.
So
maybe
sorry for interrupting.
Maybe this isn't the best thing, but I would first turn the flow rate into velocity.
That works. You're gonna need to do that, so sure. Find average velocity. Okay, so that's just, you've done enough problems here by now that you figure you're gonna need to do this, so that makes sense.
Okay. And then for finding F, do we use the internal pipe flow frictions, or the ones that we just learned with the Colebrook equation?
The Colebrook equation is, well, the Colebrook equation is what you use for turbulent flow. So first you kind of need to figure out whether this is laminar or turbulent flow, right?
Yeah, makes sense.
Yeah, that makes sense. So how would you do that?
We would find the Reynolds number.
You find the Reynolds number, and you need the Reynolds number to plug into the friction factor equations anyway, so cool. Reynolds number is equal to rho BD over mu. So that's why you were right that you needed to find the velocity, the average velocity. So once you have Reynolds number, check whether laminar or turbulent. And if it was laminar, then you would use that equation for the friction factor we talked about last week. If it was turbulent, what would you do?
Oh, sorry, I was writing it down.
I'm sorry.
I'm not sure.
Okay. So those equations we just gave, what are those?
Oh, it's the
What
turbulent.
are these equations for?
Gotcha.
Yep, these equations are finding friction factor for turbulent flow. So you would just, so let's find F from appropriate equation, so whether the one for the laminar flow or one of these guys for the turbulent flow. Okay.
In turbulent flow, are we usually explicitly given the roughness factor, or will we have to look it up?
So the most common thing is for you to be given what the material of the pipe is. So I would say it's a steel pipe, and I probably need to give you some more information about that, or it's a plastic pipe. And this sort of reflects what would happen in real life is you're working in a factory and you've ordered all this pipe. You know what material it is because that's on the description, and you need to figure this out. So you would look up the roughness factor for that material. So there's one in your book. Engineering Toolbox has one. A table of roughness factors. All would be fine. Okay. Or you might, if you want to be very specific, maybe you would need to do some experiments to figure out what the roughness factor was for your specific thing. Like if you had some old corroded pipes or some new material and you wanted to know exactly, then you might need to do experiments and measure it yourself by measuring the pressure drop and finding what the roughness factor would be. Okay. So you find F from the appropriate equation, like one of those ones we just found, and then plug in there, and then you find that. So this is relatively straightforward, actually, this one. Okay. All right. Now, this type of equation, let's have someone like Nathan Phillips. Hi, Nathan. You are writing stuff down. You can finish writing stuff down. Let's give you all a second. Okay, so now we know the length and the diameter, and we want to make sure the pressure loss is no more than delta PL. So we are trying to find the maximum flow rate that will give us that pressure loss. So we know pressure loss, L and D. Nathan, what do you think we do first?
So we have the pressure loss, right?
Yep, we have pressure loss.
Let's see. Well, I mean, you can solve the pressure loss equation to get velocity by itself, and then from velocity we can get the volumetric flow rate.
Well, let's see about that. The pressure loss equation is okay. So velocity is in here, but there's a problem. So, and that problem is something else in this equation depends on the velocity. What's that?
Oh, the Reynolds number.
The Reynolds number, and the Reynolds number tells us what the friction factor is, right? Okay, so we need to figure out what the friction factor is, but how do we figure out what the friction factor is if we don't know the Reynolds number? How do you think?
Using the Holland equation?
Use the Holland or the Colebrook equation, right? So in order to use those are for turbulent flow. But if we don't know what the Reynolds number is, do we know whether it's turbulent?
No, but we can guess, assume that it's turbulent.
Yeah, you can guess. Guessing is exactly the right thing to do there. Assume laminar or turbulent. Turbulent is usually a better guess. Okay, so you assume laminar or turbulent. Okay, and so now you know that we set up a system of equations. So we know this, so maybe our equations could be delta PL Okay. And sometimes, by the way, you would need to solve a mechanical energy balance in order to get whatever the delta P loss should be. Just like we did that earlier without thinking about how you would find delta P loss this way. Okay, and then maybe your second one would be either the Holland or the Colebrook. Let's say the Colebrook, 1 over square root of F is equal to negative 2.0 log of the roughness factor over something, 3.7, plus something over the Reynolds number. What was that?
2.51.
What?
2.51.
3.51 over the Reynolds number, square root of F. 2.51, this is what you said?
Yeah.
Okay. Oh yeah, 2.51. You can always just check your book for that. Reynolds number, square root of F. Okay, that's your second one. And then for your third one, Reynolds number is equal to rho BD over mu. You could make this be 2 equations by plugging this for Reynolds number in there. It doesn't really matter. Okay, so you set up your system of equations and then you solve it iteratively using, again, Excel or FSolve. And again, I usually prefer FSolve personally, but Excel's nice because it has a really nice intuitive user interface for you. Now type 3, you're finding diameter. So the Reynolds number, it depends on the velocity, which depends on the flow rate. It also depends on what?
Diameter.
Diameter. So we got to do the same thing. Oh, and so by the way, solve for V, then find Reynolds number, check assumption. So you want to find the Reynolds number at the end to check your assumption of whether it was laminar or turbulent. Okay. So Legrand is telling everyone that he likes to minimize the number of guess values when using FSolve. I'll show you when I show you the example of my FSolve block, how that could work. So in this case, it's sort of the same thing. You have to assume laminar, turbulent, set up system of equations, and it'll typically be the same equations. Solve for D, find Reynolds number, check assumptions. All right, so let's talk about an example in our last few minutes of class. Right, so I have made two kind of example problems here. We have, so example 1, we've got 1 liters per second of water at 20 C running through a 2 centimeter diameter stainless steel pipe. What will be the pressure drop across 1 meter of pipe? So this is the first kind of problem. It is relatively simple to solve. We would find the Reynolds number. Then we would find the friction factor, and then we would find the pressure drop. And I have done that here. So everyone can see my little anaconda window, right? Okay. And I'm going to post, I have made, what was it called? Solar example 1.5. Okay. So my code that I did, and I will show that to you now. All right, so I wrote this, and I did it both ways. I used the Holland approximation and the implicit Colebrook equation. With the Holland approximation, you wouldn't have to use code if you didn't want to. If you're using the Holland, then there's no iterative solving. You could do it all by hand and with a calculator. Okay. Which I can show you here. In option 1A, you can just solve everything explicitly. There's no solve stuff. It's fine. For using the implicit Colebrook equation, you want to use fsolve. So I defined some residual. So with fsolve, you want the residual to be 0. That's the thing you're minimizing. And so I took the Colebrook equation and I said left side minus right side, put it, that should be 0, put it there. I gave it a guess. I used 0.002 as my guess. Sometimes I use 0.001. Around there is often a good guess for friction factor. Legrand is right that minimize can get you a negative number, and the friction factor cannot be negative. Okay. So that's why I use opt fsolve from opt. I know you people use Jupyter a lot. That's fine. I just never really got into that habit. I use Anaconda. All right. And as you can see, there's like about a 1.2% difference between the approximate and the exact solutions. Remember, I said it would be around 2% or lower, so this goes with that. That's pretty simple. In this case, we found a pressure drop of about 5.05 kilopascals with the Holland or 5.11 with the Colebrook. I'm going to post this example code. Anyone have questions on this example? Okay. All right, the second one's a bit more complicated, so I want to talk about that one. So now we have water. It's running through a 2-centimeter diameter stainless steel pipe. We know diameter, and we're trying to find a flow rate. So this is that type 2 we were talking about that requires a system of equations, and I want to write down what that system of equations is. I want to make sure and write it down to make sure it makes sense and we have everything. So delta P L I'm just going to use some function of Reynolds number because it could be either one. And Reynolds numbers. And if I put it like this, then we have 3 equations. What would be our 3 unknowns?
Reynolds number, F, and V.
V.
Yep. So I like to write this out to make sure that this works. All right. You want your number of unknowns and your number of equations to match, or else it's not going to work. Either you just don't have enough equations to find how many unknowns you need, or you have too many equations and it will be overspecified. So just making sure that works out. All right. This is example 2. So I assumed turbulent flow. I got the difference, and then I use the Holland and the Colebrook, and what I would want to do at the end would be to calculate the Reynolds number to check that and make sure it was turbulent. And if we look at my code on this guy, so in this case, I made my friction factors into, I defined a bunch of functions. which usually I just define functions anyway when I'm doing stuff, but you need to do it in order to use fsolve, or it makes it a lot easier to use fsolve to solve this system of equations if you define functions. So I defined one for the Holland and one for the Colebrook. And then I also chose to find one for the velocity and the Reynolds number. And I chose to make everything a function of v dot, the flow rate, just because that will make it easier when I set up my fsolve. The flow rate is the only thing it's solving for, and that will make it easier. Okay, so I do this, and then I make my residual. I also made a function for the pressure drop. And I just set, where is it? Okay, yeah, here it is. Here's my residual equation I made. So this is that pressure loss I wanted. This is the pressure loss is equal to 1/2 rho f L over d v squared. Okay. And so you do this, it would call this one, then it would call this one to get the F. And that way I can just have one guess value and one thing fsolve is solving for, which is nice. Okay, and then I did it in the Colebrook. This is a nice example of how you can put an fsolve inside of a function, which is really nice and very useful. Okay, so I'm going to post both of these on Learning Suite underneath the slides for this lecture. And you can look at it. For your homework, you're going to do one problem that involves both these types of problems where you have to find pressure drop and you have to find flow rate. And then you're going to do a problem where you have to find diameter. And I didn't do an example on that on purpose because I don't want you to just copy my solvers. I want you to look at them and figure out how to use them to do stuff. All right, questions?
I have a question. So I just put it in the chat, but so the homework that we get today then, is that due tomorrow before class?
No, it's due. I made both of the next two homeworks due Friday because I don't like you only having one night to do a homework. So both homework 11 and homework 12 are due on Friday.
Happy day, thank you.
I will send out an email telling people that because some people may have left at 11:50 and I want them to know too. Okay. All right. So I anticipate you will come to either my office hours or the TA's office hours to deal with setting up these solvers. That's fine. Yeah, that's fine. We will be happy to answer especially conceptual questions about how they're set up. And here at the beginning, I'll help you debug. Eventually, I'm not going to help you debug. So.
What time is your office hours again? 2, I think?
2 o'clock. 2 o'clock. Every day.
Hey, Dr. Nickerson.
Yes.
Can we go back to the slide real fast of type 3 of how to solve? And maybe I can take a screenshot.
About the cells.
Sorry, type 3 of how to solve the equation.
Oh, this one.
Sweet. Thank you. 1 second. Okay, got it. Thanks.
That's a better word for it.
All right.
Dr. Nickerson.
Yes.
So with the research meeting today, it's Monday schedule, so I have a class until about 5:40. Right. So
okay, thanks. You can just skip it. Yeah.
Okay.
We'll let you know if we want you to do something. We'll yell at you about it.
Okay, sounds good. Thanks.
Thanks. Right, I'm gonna stop the recording.